So, good morning, everyone. Today I'll be covering masked autoencoders in my discussion part two. So, masked autoencoders uses the key idea of mapping parts of input image and then trying to reconstruct them. It is very similar to the BERT model in NLP, which uses the concept of masking. If we see the network architecture, it uses vision transformers as it is difficult for a normal CNN model to integrate these mask tokens. Also, another thing to note here is like images have a very high spatial redundancy. This means that we need to mask images with a very high masking ratio. Unlike what we do in language modeling, where the masking ratio is low, like 10 to 15% only. This is because if like here we keep the masking ratio less, then actually no learning will be done here. Also, the encoder and decoder network used here are asymmetrical in design. Now, we will look further into the architectural details of it. So here, basically, we first divide the image into a number of patches of equal size, and then a subset of these patches, generally 75%, is masked and the remaining are sampled and passed to the encoder network. Also, another thing to note here is like uh, compared to a normal image processing, less compute and memory is used here, as we are dealing with only a small subset of images. Now, the output of this encoder network, along with the mask tokens, are passed to the decoder network. It is also ensured that the patches are passed in the correct order as in the original image. We do this with the help of position embedding. Now, image reconstruction is done here in the decoder network, and this is done during the pre-training phase. The last layer of the decoder network is a linear projection whose number of output channel is equal to the number of pixel values in the patches. Now, this output is reshaped to form the reconstructed image back. Now, coming to the loss function, mean squared error is used here to compute the loss between the original and the reconstructed image. Also, another thing to note is we apply loss only to the masked patches and not over all the images, like all the image pixels. Now, here in this plot, like we can see how different masking ratio is affecting the performance of the model. So basically, comparative analysis is done for both fine tuning and linear probing. And we can see that for fine tuning task, a range of masking ratio between 40 to 80% gives good accuracy. While in case of linear probing, the accuracy increases steadily with the masking ratio. On the left hand side, my y-axis represent this ImageNet 1K validation accuracy, and my x-axis is my masking ratio. So this analysis was done on ImageNet 1K dataset. Okay. Okay. So thank you.